Hello there. Welcome to the demonstration of our final year project. We are Group 15. We have developed a battery management system to mitigate voltage violation in the low voltage distribution network occurs due to excess rooftop solar generation. So let's look through what are the motivations and interests behind choosing this project. There is an existing issue of hosting capacity limitation in the LV distribution feeders in Sri Lanka. If the PV generation is greater than the local demand at the point of common coupling, the excess power from PV inverters may produce reverse power flow in the feeder that would create voltage rise. Due to that, further addition of grid-tie rooftop solar are limited by the authorities. Therefore, this is a barrier to the renewable goals of the country. Let's talk about the objectives of our project. We are expecting to mitigate voltage violations occurring in the low voltage distribution feeder. Upper limit of the PCC point voltages in the feeder will be maintained at or below 1.06 per unit as per SLS 1522 standard of 2016. Also, we are expecting to increase rooftop solar hosting capacities. This will be done by distributing solar generation throughout the day, avoiding voltage peaks. Our implementation also provides centralized control to the utility in managing voltage. Real-time monitoring is an additional advantage. Prevailing method of inverter tripping to avoid voltage violation fails to limit the voltage at higher hosting capacities. Our implementation will prevent energy losses during inverter outages. Let's quickly dive into the theoretical aspect of the problem. We can easily understand the reverse power flow and the voltage rise using a phasor diagram. First, you can see how the forward power flow through the distribution feeder with the blue portion of the diagram. The red portion of the diagram shows the reverse power flow. This illustration is made by assuming unity power factor for generation and consumption. The operation and control strategy of the battery management system. Our implementation has mainly two parts, which are central control unit and the battery management unit. Central control works as the brain of the system, deciding how each battery management system, BMS, should be dispatched. Shown are the control steps taken by the central control algorithm to mitigate voltage violation occurring in the feeder. The central control monitors the voltage at each consumer PCC at regular time intervals. It decides the individual BMS dispatch level according to the voltage profile of the feeder. If voltage at any point in the feeder is greater than 1.05 pu, central control will run its algorithm to control voltage from increasing further. The BMSs in the feeder are arranged in descending order of their PCC voltage. The first BMS in this list is assigned a charge rate which is 10% of its PV system production. The algorithm checks the effectiveness of this decision by performing a load flow analysis using a built-in feeder model. The algorithm will choose the next BMS in the list and assign a charge rate of 10% of its solar PV system production if the prior decision was not enough to lower the feeder voltage below 1.05 pu. This will continue until max feeder voltage is less than 1.05 pu. After assigning all BMSs with charge rates, the magnitude of the charge rate will be increased to lower the voltage in the similar order. It has been decided for any voltage below 1.045 pu, dispatch charge rates should be decreased, and if voltage is sustained below 1.045 pu, battery should start to discharge. Our control strategy is used when there are many grid-tie solar PV customers in a particular feeder. Consumer connection diagram shows how the control strategy is physically implemented. Ultimately, all BMSs will be connected to the central control. Let's see what we have developed in MATLAB and OpenDSS environment. This is the MATLAB script, which has OpenDSS integrated into it to perform load flow analysis. Battery Management System Design. This is the schematic diagram of the battery management system that we have proposed. A PV array consisting of 2 strings of 3 modules is used as the power source. In order to obtain maximum power output from an PV array, a maximum power point tracker is introduced. The MPPT controls a boost converter to adjust voltage. The output of the boost converter is connected to a DC bus. The battery is connected to this DC bus through a bidirectional converter which acts as a charge controller. The inverter is also connected to the same DC bus bar, and it operates in the MPP voltage range. The inverter modeled is a typical grid tie inverter that can be found in most rooftop solar PV systems. The inverter uses an indirect current control technique known as DQ control for generating the required frequency and voltage amplitude. The design and the control strategy is stressed to check the stability. The feeder model which we have chosen to implement is located in Kalubovila. Feeder pole locations, customer load data and other essential data was obtained. These are the customer load data profiles. They are categorized according to the monthly consumption. And the solar PV profiles were obtained using the PVsyst software model. The design was stressed using different PV penetrations. Here you can see the data for a sunny day and cloudy day. The results of the project. Here is a real-time monitoring of the voltage level along the feeder, with and without voltage control. You can see the difference between the voltage level clearly. This is done considering sunny day. Again, this is the same real-time monitoring, this time it's done considering cloudy day. The BMS responds to the different charging and discharging signals. The graph illustrates the BMS response throughout the day. And here we manually controlled the BMS to check the responses for the demonstration. This concludes the demonstration for our final year project. Thank you.